Welcome to video 4.19. This is the last video of section 4.6 in your text. And as you can see by the title, we are going to review major equations for PCA, many of which, well, all of which are comparable equations for factor analysis. And we'll see through this video that PCA is simpler and more direct computationally than factor analysis. So for factor analysis, we had an equation. In your text, it's equation 4.4, in which we did the factor analysis transformation from manifest variable z-scores into factor scores. For PCA, we have a similar transformation, and it's given in equations 4.13a and 4.13b in the text, which are the ones on the left here in the green, and then the one in the blue right below. And in these, we are going to, the top one, we're going to transform uncentered raw data into uncentered component scores, and then the blue one down here, we're going to transform centered raw data into centered component scores. So you see I've entered the raw data and then the centered data here, and I have K here, which is our normalized eigenvectors matrix. So once again, this is a review. So from video 4.13 we showed this, but simply we're going to do matrix multiplication the whole time in this video. MULT, we highlight the matrices with the comma in between, and then do Control-Shift-Enter. And you'll see this corresponds with the numbers in your text. And we can do the same thing for the one below to get centered component scores. And once again, we see that this is the raw data x centered around its mean, so the deviation from the mean. Now luckily, this transformation is reversible. Now you won't find this actually happens too often. This is reversible when enough components are extracted to account for all the variables. And as you know, as you see here, we have a rank of 2 matrix. So we can reverse it with the equations to the right. So you see I have put the scores in for our y matrix here, which we just calculated, just transferred over, and the matrix, centered y matrix over here. And then we're going to post multiply it by k transpose. So let's do that. And you see that the scores come out as our raw data that we had before. And if we do this one below, you'll see that we get the centered scores here that correspond to what we have over here. And this was from video 4.13. So once again, this is just a review. Now if we move on to the next sheet, you'll see at the top, for PCA, the scaled coefficients K sub SC, that's the K matrix, the scaled coefficients, are the matrix square root of the covariance matrix S. And this is equation 4.16 in your text. And I've already entered the scores just to make this video go a little quicker for y'all. But you can see I've gotten these from table 4.8, video 4.15 talks about this. So if we do matrix multiplication here, we should get our covariance matrix. Which we do. You'll recall this is the covariance matrix. I went ahead and put the numbers down here in this next equation, which will show us that the coefficients matrix K, or the normalized eigenvectors, can also be used to transform the covariance matrix S of manifest variables into the covariance matrix of latent variables, which we call lambda, which is the diagonal matrix of eigenvalues. So we can show this here. I'm going to do this all in one equation, MULT, and then M-M-U-L-T. What I'll do is I'll highlight this one here, comma, our S matrix, then a comma, and then K. That should be good. And you'll see these numbers correspond with the numbers in your text. And this was from video 4.12. And of course, when all the variance is accounted for by the extracted components, as is in PCA, this process is also completely reversible. One can use matrix K, which I have here, to transform the covariance matrix of latent variables back to the covariance matrix of manifest variables S. So we should get 4, 16, and 22.4 on the diagonals of this one. And I'm going to do this all in one shot. And you see that it is completely reversible in this case. And this also goes back to video 4.12. So before I mentioned that PCA is a little more simple than regular factor analysis, and one reason is because factor analysis uses 3 forms of the eigenvector matrix. They call it K, F, and T. So that can get a little confusing, whereas PCA only uses 1, or K. Although, as you see, for some purposes, we use the scaled form of the coefficient. So we have K sub SC. So we see that PCA is simple and more direct compared to factor analysis. It also involves factoring a covariance matrix as opposed to the correlation matrix, which factor analysis does. Its intent is to create linear combinations of the variables that are orthogonal to one another, meaning that the latent variables don't correlate, they're independent. And when we create these linear combinations of the variables that are orthogonal to one another, we account for the maximum amount of variance in the original variables.